All right. Hey, welcome back. Today we're going to talk about array lists. But first, we're going to go back and we're going to finish our arrays example a bit. I have made some changes this time around. Arrays example is on the left, and then the array list example that we're going to put together is on the right. The first thing that I want to talk about is how we would actually grow the underlying array, because we never actually set it, at least in code. So how do you make the underlying array bigger? Well, remember we have this array that backs all of our data that we declared at the top, and it is initially sized right there in the constructor. And after that, it is the same size until it fills up, and then when it gets full, we were just printing out this error message like, hey, it's full. So how do we update the size if we want to? So I've written this grow function here, and I never saved the size as a variable, you can see up here. So in order to get the current length of the array, we had to grab it again. So the current size is the length of the array. And then let's say I want to make it 1.5 times bigger, which is basically what ArrayList does under the hood when you run out of room. So the new size is going to be 1.5 times that size that we currently have. What we're going to do is we're going to copy the original array, which, by the way, I've also turned into an array of items instead of an array of integers. I will go over what items are in a second, but that's not really that important right now. And the way I copied it is by using a built-in function called clone. You could also have copied it with the for loop. I'm sure everybody remembers how to do that, but we're going to do that actually in the next step here, so if you don't quite remember, you'll see a little bit of how that's done. Clone is giving you an exact copy of that original underlying array. And then I've created a new array and just basically saved it over top of my existing reference to the array. So I made a copy of the original, that one's the copy, and then I saved over the original with a new array that is larger, that is the new size. But this new array does not have any of the original values. It's just a blank array of the new size. So now I've got to copy all those values over. So I am filling up the new one, which is still named R, and I'm putting the values from the copy into R. And I'm looping over the original size of the array because the rest of it doesn't have any information. So I don't actually have to loop up to new size, I only have to loop up to the original size. If it was full, then anything beyond that obviously doesn't have any data yet. But that isn't enough, because if I just did that, then the rest of the spots, because I made an array of items and not integers, they wouldn't just be empty, they would be null. And of course we don't want them to be null, so I went and instantiated a bunch of items in those remaining spots. And there you go. The only remaining step was to inform the display that a new array demo had occurred, and the easiest way to do that was just to recreate the display variable as well, but we're not going to talk too much again about the display code, so just take that for granted. Next up, let's look at what an item is so that we can remember this for the array list example. So I was using basic integers when we were talking about arrays last time. And that's fine and dandy, but if we want to get a little bit more complicated, we want to store things that are more interesting than integers usually. And so I modified the original array example. I won't go over it, but you can go and see the modifications that were necessary to get it to use items instead of just integers. Now items have this int value, and all of the sorting and removing and inserting is done based on the value, at least in the arrays example. We'll do some sorting, inserting, and removing based on items instead. And then each item also has a name, a little extra value where we might put some other information. I just have a function that sets it to a random value. If you only want to specify a name and a value, it'll set that extra to a random value. We won't use the extra today. But if you wanted to, you could now print out all of the names of all of the different items that you had created, and each of them is supposed to get a unique name. And it also picks a random color, and this allows each individual item that we put in our list to be drawn in its own color when the display renders it. So now when things are added or removed, instead of the color being bound to the individual box, which was what it was like before, the box at spot 0 was always one color, the box at spot 1 was always another color. Now we can actually watch the items move around because each item has its own color. And we'll see this on the display, that as we add or remove things, the color that each individual number is will stay the same because the color and the value are now together in this object. And the only other addition here, let's see, where am I at in the file thing? The only other addition here is that to generate the names, I wrote this name generator class where I just have a list of possible names and it will pick a random one for every item that I make. So when I use this later on, just remember I wrote this simple function to give you a random name from a list of a bunch of possible ones. And I don't think we'll use the name today either. I think we'll just stick to the value of the item and we'll use the color as a reference so that we can remember that each value is paired to a color, and as we add or remove them, you can see which value is getting added or removed by linking it together with its color. Alright, so with that, let's go back to the array demo for a second and look at when we use grow. So anytime previously when we had inserted and we were out of room, we printed this error message like out of space. Anytime we were going to do that, instead we would grow, and now we have more room to insert the thing that's being inserted. Now I did this a little bit poorly because I left the return in many places where we were previously printing that error message, so where it was telling us that the array was full and unable to do it. So the first time you try to insert something, it'll actually fail, it'll grow the array, and then the next time you do it, it'll actually insert. I'll leave it to you to figure out how to change that code so that it actually grows and inserts in the same operation. But you'll see that grow has been added to all of the different insert functions so that they now expand in size instead of just telling you that the value was unable to be inserted because it was full. And that actually gives us what is basically an array list. Now, you should have learned about array lists in your previous object-oriented class. If you haven't, that's okay. We're going to go over most of the basics here. Oh, one other change that I made that we're not going to talk about is that I made this interface that ties the two demos together. So this is what both the array and the ArrayList demo have in common. This is used for facilitating the display of the boxes. And again, we're not going to talk too much about the display. Okay, with that all taken into account, we're going to go back to the display demo. I've also turned the array of rectangles that underlies the display into a array list as well, so that you can see how to maybe use that in Swing too. Again, we won't go over that. And if we go back to the display, we'll see that I have now created an ArrayList demo instead of an array demo. So moving forward from here, we're going to be on the right-hand side of the screen. We're going to be talking about the ArrayList demo. Okay, all of that housekeeping out of the way, let's begin to talk about arrays. We have the same kind of stuff at the top. We have that is sorted that I still poorly kept in the display, whatever. We have a constructor. We have now use alt instead of, I think I called it use better or something for the array demo, but when it comes to the array lists, it's not really better or worse for the examples that we're going to go over. It's just different situations that you'd find yourself in inserting and removing. And I still have that placeholder for a failed search. I'm still going to return -1 if a search is unsuccessful, but I don't have that default. So I don't have that default value anymore. If a spot is empty or unavailable, then it can be null, or it might have a placeholder value. We'll look at that in a second. First, let's look at how to declare an array list. You'll see a little piece of syntax that you're probably unfamiliar with here. You'll see these little carets. You might have seen these, you might have not. The carets tell you what kind of array list that you're making. So are you making an array list of integers? Are you making an array list of items? Are you making an array list of records? Whatever. So that's basically the name of the class of the thing that you're making a list of. So in this case, I have a class called item. Remember this guy, the name, the value, the extra, the color. I'm making a list of those. If we go back to the array demo, that echoes this declaration above where I made a list of items. I made an array of items. So since this is not, how should I put this? Since you can't just say private item ArrayList, you can't like combine keywords like that. The way that we decided to do that in Java and in many other languages is that you include these little carets to say what kind of list that you're making, but the primitive, the array, doesn't require those carets because it already has its own, let's call it custom syntax. But you can sort of think of arrays as fundamentally doing the same thing here. Okay. While this declares the array list, much like for an array, it has not yet instantiated it. So we are not yet ready to add or remove things to the array list until we actually instantiate it, which happens down here, where we declare new array list, and it creates one for us, and it always creates one for us that is empty, although you can create one and add some items to it right away. But for this example, we're always creating one that is empty. And array lists can be created with no argument, like this, or we can take a size argument, as I've demonstrated right here. If you create one with no argument, it simply uses a size argument of 10. And all this does is it tells the array list how long the underlying list should be. So remember that underlying the array list, there is an array that's expanding just the way that we wrote it when we wrote the array demo. And if we specify how long we think it should be, we're saying that we think we have about this many items. If we guess incorrectly, that's fine. But if we have 1,000,000 items and it defaults to a size of 10, then it's going to have to multiply itself very many times. Remember, it's going to expand to 1.5 times its original capacity. That means the first time it's going to grow to 15, and it's going to grow to 23 or whatever. And so it's going to take a long time, many, many copies to get to 1,000,000. And each time we run out of space and we have to do this grow operation, well, it's obvious that this grow operation is O of n because we have to copy all the items over, and that takes a significant amount of time. And there's also extra overhead associated with allocating that extra memory. So this isn't an operation that we want to do a lot, and so it's best to specify a size that's close as possible to our final kind of amount of items approximately, or at least the same magnitude of items that we're planning to add. And then it's also a bad idea to say like 1,000,000 here because you don't want to use up a bunch of memory when you don't have to. So if we're only adding something like 10 items, much like you wouldn't instantiate an array that's 1,000,000 items big, you don't want to do the same thing for the array list. All right. So I specified a size here, and in the display I passed 5, so it's going to start out only supporting enough capacity for 5 items, and then we're going to see it expand. I've added to the display a bit, and the demo display will now show you how large the underlying thing is. Now, one thing to point out is that array lists actually don't give you access to the underlying array. This is by design. It's so that the developer can't shoot themselves in the foot by accidentally modifying it. So I'm actually just making, I guess you can say a guess. I'm just following the times 1.5 rule, but it actually might not be totally accurate with the true expansion of ArrayList. I don't know, for example, if it's still 1.5, maybe they've updated that in a newer version of Java, whatever. So the display isn't exactly the law here. It's following along with it, but by design you can't access that underlying array. And you shouldn't be able to, because it only leads to confusion when you're working with an ArrayList. You have no reason to access it. Let's begin with let's begin with the most basic kind of insertion. Let's go with, let's see, let's start with, let's start with inserting unsorted at the end. Okay. So to insert a new item unsorted at the end, this is the most basic and the most common kind of insertion. Let's create an item to insert first. Remember, we're dealing with items now instead of with just integer values. So we're going to create a new item. I'm going to invoke the, what did I call it, the name generator to get a random name for this item, and then I'll use the argument that was passed here for its value. So that's going to pick a random name from the list of names for the name. It sets the value to n, and then it also has that extra value that we're not going to use, which is a random number, and then it also picks a color, which is a random color. Okay, I want to add this value to my array list. Pretty easy. r.add, and then the item that you want to add. And it's as simple as that. And this is actually going to add it to the end of the array list. And so just like our unsorted insertion in the previous array example, this is going to be O of 1. It simply adds the item to the end of the list. However, it is O of 1 in what we call amortized time. I think I spelled amortized correctly. I might not have. Amortized time. Amortized. And the reason that we call it O of 1 in amortized time is because on average, the vast majority of the time, it is O of 1 to add something to the end. But occasionally, that is when the list is completely full. When the list is full, it's O of n because we need to copy all of the items over. And so one characteristic of using very large array lists in your program is that you can very occasionally generate small performance hiccups as the array list has to grow and therefore incurs this very large O of n overhead to copy all the items over. But you don't really see this much. It's not enough of a performance issue to generally affect the performance of it such that the end user can see it, unless you're dealing with very large array lists or a very slow machine. This happens so infrequently compared to inserting items the rest of the time when it's O of 1 that we still say that the performance of array lists is O of 1 in amortized time. But if you really wanted to do the math, right, to figure out exactly how much is it, well, okay, most of the time it's going to be constant, so 1. And we could say that, let's say 1 out of n times, really, it's n. So 1 out of n times the performance is n. And then the remaining n minus 1 over n times, it's O of 1. So if we really wanted to break it down, it would be something like the sum of these two. So it would be something like n minus 1 times 1 plus, and then 1 over n, well, it would happen 1 time, so it would just be plus n. And then that would be divided by the number of insertions, which was, let's say, n in this case, so we've inserted into every spot. And if you break this down, it gives you about approximately 2. And 2 is a constant, so constant time, more or less. I'll leave a longer comment for that if that math was confusing to you, but keep in mind that n minus 1 times, it's constant, and then just 1 out of n times, we need to do that full copy in order to expand it. And as n gets bigger, obviously there are more and more spots before we fill up. Okay, that pretty much settles it for the insert unsorted. There is one little piece of housekeeping that you need to do to update the size of the display, those little black bars that are going to delimit the sides. So you do have to call this extra here, but part of the display, so we won't go into it. And let's see, that was insert unsorted, which was the not alt version. And I specified that is sorted as false, and use alt as false, so this should use the correct one. Let's run it and find out. Alright, so there's 4, 5, 6, 7, 8, and then it's full. What happens when we go to insert the next item? Let's put in a 3, and lo and behold, our 5 item list is now 1, 2, 3, 4, 5, 6, 7 spots large. It's grown, this black bar moved to the side, that's why we needed this extra line here. And that's also why we needed to update this extra line here. And let me fill it up again. Let's add another item and then one more, and as we can see, it's now grown to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items large. Next time it will grow even more, and even more, and even more, and even more, and so forth, infinitely. And all of that copying and stuff is handled for us completely under the hood. This line doesn't do any of that stuff, I assure you. That is all actually handled as part of the add. Every time the array list grows, if it's reached its max size, it'll automatically expand itself for you and add the item without you having to do anything. So unlike our previous array demo, which had us have to write our own grow function, where is that at? It doesn't matter. Anyway, the grow function is now handled completely under the hood for us, and we don't have to worry about it. Okay, well, that's how to insert something in O of 1 time. Let's look at another way that we could insert something. So I'm actually going to copy all of this stuff and look at the alternative r.add function. There's another one. So if we look at the documentation as we type r.add, we'll see the r.add one that takes the object that we want to add as an argument, and then we see one more that takes an extra argument. It takes an index and then an object. You can use this to insert at any index. So let's say I want to insert at the front. That allows me to say 0, and then I want to insert at the the item at the head. So if I'm inserting at index 0, then I'm inserting at the front. And this handles all of the shifting for you. Inserts at the front of the array, well, let's call it ArrayList to be consistent, it handles all of the shifting for you. But this, of course, is not O of 1 because the items have to shift over. And because the items have to shift over, this is not O of 1, but rather O of n, just like our shifting array examples were earlier. Often you'll see this mistakenly referred to as O of 1 in different examples on the internet. This is one of the more common mistakes I think that you see in guides to an array list. But this is O of n because, again, the items have to shift, and we can clearly see this if we set our useAlt to true so that it trips that one instead, and then run it. We can see, let's add a 7, let's add an 8. You can see that the 7 had to move over to accommodate the insertion of the 8. If we add a 3, again, the 8 and the 7 had to move over to accommodate the insertion of the 3 at the front. But all of that was handled under the hood for us by this adding to an index argument. Some people find it hard to conceptualize that it adds it at that index. So, for example, some people might expect that if you wanted to add, like, to the front, you would have to say -1 or something. And if you're not in this headspace, try not to get into it. Maybe I shouldn't have even mentioned it. But telling it to add at spot 0 is telling it overwrite spot 0, basically move everybody else to the right. So if you want something to actually appear right there, for example, where the 7 is, then you're going to add at spot 0, 1, 2 specifically. The 7 would shift over to make room for it. Now if you called r.add and you specified one of these tiles on the end, then nothing would have to shift over. So of course this would still be O of 1. But whenever you call r.add and you specify an index where items have to shift over, that becomes O of n. So generally speaking, we should refer to this function as O of n, and at least n over 2 on average, right? If you picked a tile at random, it would be about n over 2 on average. And it still works for expanding it. So as it reaches its max size, I'm adding 1 to the front here, and then adding 2, and it's still going to expand itself. And all that other functionality, again, handled for you under the hood. So if you wanted to reproduce the simple add to the end using this and keep your O of 1 time, you could simply do r.add and then r.size, which would add it to the end here. And this works because r.size does what you would expect it to do rather than returning the length of the array. What it does for you is it returns a value that we're familiar with from last time. It returns for you the next spot. So r.size doesn't give you the length of the array list necessarily. It does because array lists don't have any gaps. But what it's really giving you is that next spot value, because the length of the underlying array is different. That's got some empty spots in there at the end. But we don't care about that most of the time. We care about the number of elements in the list, and that's what size means. And that's also why they didn't use length here. They used size, because it's different. You're not getting the length necessarily of the array list. You're getting the number of elements in it, omitting the fact that there are actually these invisible, to us, blank spots on the end under the hood. No, we're getting the number of items in it. So it always gives you the address of the last available, or the next available spot, too. And let's go back to our insertion examples and continue. So we've done 2 unsorteds. Let's do some sorteds now. Let's do some sorted examples. Okay, so the first sorted example I'm going to do will be very similar to the first sorted example that we did for the array demo. So let's pull that guy up. Let's find this one here. The insert sorted. All right. If you look at the original that we did for the array, it's pretty long. And it's pretty long primarily because we had to find the spot we were going to put it into. We had to accommodate the case where we found nothing. We got to the end and we found nothing. And we had to shift all the existing values in order to make room. Well, we know that we probably don't have to shift. Let's see if we can pull it off without having to look at the end either. All right, so I'll copy this item declaration over, and I'll copy this line where we update the display over. Those are going to be the same. All right, so first I need to find the spot where the thing belongs. That's the same, and just like for the array example, I'm going to bake the search into the insertion algorithm, although again, technically we don't usually consider the search to be a part of it, but it is a part of it, and it's important to note that. You obviously want to prefer an algorithm that doesn't need to search to insert versus one that does, so it does matter that you have to search. Anyway. Let's look at how we might loop through the array list in order to find the first spot that is bigger, which is exactly what we did here. So here we did while k is less than r.length. Here we're able to be a little bit more efficient. So while I is less than r.size. Remember when we wrote this one back then, I said, wouldn't it'd be a little bit more efficient if we only looped up to the next spot instead, because beyond that point there's just blanks. Well, here you go. You can basically do that automatically with an array list because there are no empty spots at the end. The size argument only gives you up to the last available item. And I'm going to bake into the while loop directly r.get, and then this is to return the value at some index. Remember, we're working with items here, so to get their value, I have to do .value. While that's less than the value that I'm looking for, I'm going to increase I by 1. So that's an optimization I could have added to this loop here, but because I had to look for the spots on the end, and I didn't make that optimization where I only looked up to the next spot, I had to write it a little bit in a more complicated way. And if you think about it, if I had made that optimization to loop up to the next spot, then I would still have a little bit of complexity because I would have to check inside the body of the insertion function that we hadn't filled up the list, so that we hadn't gone out of bounds. After I added this growing functionality, that wasn't a problem anymore. But in the original implementation, where it was possible to go out of bounds, I would have had to do that. But not here. The growing part is handled for me. The size argument gives me the next available spot already, and so I can just bake that right into the body of the while loop there. So I'll just keep moving on and going to the next index while I haven't found the value that I'm looking for, and then when this loop ends, I must be at the first spot that's not, the first spot that's not, not smaller. It must be at the first larger spot in the array list. So if it was something like this, if it was 1, 4, 5, 6, 7, 8, 9, and I was trying to insert, let's say I'm inserting let's go with 6, okay? While I is less than r dot size, I equals 0 at the beginning. Okay, while I is less than r dot size, that's true. The size is 1, 2, 3, 4, 5, 6, 7. And r dot get I dot value is less than n, so that would be 1. Is it less than 6? Yes, so we move on to the next one. That would be 4. Is 4 less than 6? Yeah, we move on to the next one. 2. Is 5 less than 6? Yeah. So we move on to the next one. That's 3. Is 6 less than 6? No. So at this point we terminate. That gives us the spot to insert into. It's going to be right there. And so we want to insert the 6 like that, scooting the other items over. It's the same functionality again that we did here. We're looking for the first value that's bigger than the one that we're looking for. And if we don't find it, think about what happens. So actually, let's load that back up and assume that it doesn't exist. So we have something like that instead. So we pass this 5, and it's not there. And we go to the next value, we get to this 5, and it's not there. Then what happens is we violated this condition on the while loop. The I is now greater than the size of the list. And then when we do the insertion, we'll just have inserted onto the end. Okay, so let's do the actual insertion. What do? We want to add the item. Let's think. We have this functionality that adds things at an index and scoots everything over to the right, remember? Let's just use it. Why don't we use our add functionality that already exists that adds the item, scoots everybody else over to the right. And in the case where we got to the end, well, that's basically the same as adding it onto the end. It's just going to add it to the last spot, so the next spot, if you want to think of it that way. All right, so let's give this guy a shot. I need to change some stuff. Let's see, where's my insert function? I got 2 this time, so I want to use alt, yeah, I think. Yeah, all right. And I want to set is sorted to true. All right, and let's give this a shot. So 4, 5, looking good so far. Let's try to add a 1, and it goes in front of the 4 and 5. Try to add a 2, goes between the 1 and the 4, a 3, where it's supposed to be. Now look at this 3, it's blue 3. Remember, the color now corresponds to the actual item. What's going to happen when I try to add another 3? Well, remember, tie breaks also end the loop. So what it should do is should add the new colored 3 in front of this one, and it does. That nice pink 3 is added in front of the existing one. If we add another 3, it should be in front of that pink one again. Remember last time I said that when you're doing these kinds of algorithms, you should also think about what happens when ties break. So in this case, it inserts before. And that's fine because we haven't specified a requirement for it to do otherwise. All right. That's one way to do sorted insertion. But it was still a little bit complicated. It was definitely a lot easier than this guy because we didn't have to do all the right shifting manually. We didn't have to accommodate for getting to the end and find nothing bigger manually. We didn't have to accommodate for going out of bounds. All of that was handled by this for us. But we can actually go even simpler. So copying those 2 pieces of boilerplate again, I can actually merely add the item. Okay, and then I can call the built-in sort. Call the built-in sort. And once I call the built-in sort, it'll put them back in order for me. Now, the built-in sort, remember we talked last time about the built-in sort for arrays. The built-in sort for ArrayLists is similar. It's also about O of n log n performance, I think. We'll read the documentation for it. Actually, I don't think it tells you. But you'll notice that I have an error here. It's because in order to sort a list of items, these aren't integers, right? It needs to know how it is that you want to sort them. What's the sort criteria? And that requires you to write something called a comparator. So we'll do that now. We'll write a comparator for this. And then we're going to use this again when we write the sort function down here. I think there's one down here someplace. There we go, there's a sort. All right, so let's write it here as well, and then we'll go back up for it. Okay, a comparator is a very interesting syntax that you probably haven't seen before. A lot of people will declare their comparators inline, so don't be surprised if you see that. I'm going to declare it outside of that function because I think that it's a little bit cleaner, especially the first time you're seeing it. So, comparator, spelled like that, like the array list, it needs a type, so in this case an item. And this is going to tell you how to compare two items together and determine which one should go before the other for ascending or descending lists. And I'm going to call it compare values because this one is going to compare the value trait of items, the one that's a number, remember. Alright, so I take an array list of items as an argument. And you'll have to import comparator. There we go. And then it'll keep having this error here, and it wants me to add a return statement. Okay, well, that's not helpful. Return null, right? I want to return a comparator. So let's do that. Let's do return new comparator item. That's actually what I intended to do. And then it's going to continue to complain. So now I have a new error, but this is better because now it's telling me add an unimplemented method. Okay, well, comparators inherit from this comparator built in, and they need to implement at minimum this one function, compare. So all of this was a lot of song and dance to get to this one function, which takes two items as an argument, a first item and a second, 1 and 2, and then you have to tell it how to decide which item goes first and which item goes second. And if we read the documentation for compare, it gives us a tip on how to do this. So hovering over this, I think I gotta fix my missing. Right there. Yep. All right. There we go. If you hover over it, it'll tell you compares two arguments for order, returns a negative integer, 0, or a positive integer, if the first argument is less than, equal to, or greater than the second. So respectively, if the first argument is less than the second, you want to return a negative number. If it's equal, you want to return 0. And if the first argument is greater than the second, then you want to return a positive number. And if you flip those, then you'll get descending order instead of ascending order. So to satisfy this, all I would have to do would be to return O1.value minus O2.value. Conceptually, let's think about this. All right, if 1's value is larger than 2's value, then it returns a positive number. And remember, returns a positive integer if the first is greater than the second, is what it told us to do. If the second item is bigger, it will return a negative number. The magnitude, by the way, doesn't matter, just that it's negative. And if they're equal, then this will return 0. So this satisfies all of the requirements of the compare method that we were supposed to do. You can also compare things that are not numbers by simply assigning them some kind of numerical value and then using those same directions, returning a positive number, 0, or negative, depending on whether you want the first one to be after, at the same level, or before the second item, when you go to sort them into order. Alright, so that's the comparator done. Now we can tell our sort to use that comparator to sort. So if we give it an argument like that, it will now use our comparator to sort. All right, actually don't think we need this bit here, do we? Let's have a look. There we go, lovely. So we actually don't even need the ArrayList arc. All right. And then likewise, we'll go back up to our Where did I call it? This guy. And we'll also use the values to sort the list too. Okay, so in order to insert something in sorted order, simply added it to the end of the list, and then called the built-in ArrayList sort, told it the criteria that I wanted it to sort by, so basically what is bigger than what for ascending and descending order, and then it will execute under the hood its sort, which is about n log n time, and put it into order. So this guy is still probably faster overall. Okay, I don't think we need that. This guy is still probably faster overall because it's finding the spot and then inserting just in the spot and shifting just the values that need to be shifted. But it's about O of n to find the spot, and then it's about O of n to shift them all over. So in some instances, this one might actually win, because that n log n performance might actually be faster than finding it and shifting the values over. Alright, let's use it. I think we have to set this to false. Let's see, that's going to trip our insert sorted alt, which is this guy. Great. And let's see if it works. 8, 7, 4, 5, 0, 1, 2. You don't see the sorting happening, obviously, because it all happens so fast, and because our display only updates when it's finished. Our display updates very, very quickly on a modern machine. So you never actually see the sorting happen. You just see the finished product under the hood. But that is, whoa, didn't mean to make that big. A much easier implementation to write than this one, and not substantially less performant. Alright, so that does it for insertion. Let's go move on to removal. Removal in ArrayLists is a little bit more challenging than insertion is. Alright, let's start with removing an item. Alright, so you can specify a value, like we're going to do for some of the rest of these, where we want to find the item that has that value and remove it. But of course, you could also just specify an item. Remember to be careful with these comparisons in Java, because the items have to be an exact match. Just because both items have a value of 5, and they both have the same name, like Bob or something, that doesn't mean that they're necessarily exactly the same item. You might also refer to the fact that they have a different color or a different extra value, but even two objects that have exactly the same values, exactly the same name, exactly the same color, those are still not necessarily the same object. So be careful, because when you're removing things by object reference, it actually does have to be exactly the same object. Alright, this is very simple. We can just do r.remove and then pass the object we want to remove in there. This is going to be O of n, because it has to search through the array list, which by default is unsorted, and under the hood it always assumes that it's unsorted. So we'll have to search through all the values in order to find it. We could make this a little bit faster if we manually sorted our array list. We could find the spot with a search, like we're going to write later, and then we could remove it after we found the index. So could do a little bit better there, but generally speaking, you're going to incur O of n to find it if it's unsorted, and then you're going to incur O of n again to remove it, because again, all the items have to shift to the left. So that should be pretty straightforward. Okay, let's start with remove value bad next. And we'll start with removing something by value in a bad way. Now, if we had this function, I want you to keep this in mind. And another thing I want you to keep in mind, actually, before we move on, is that it returns a Boolean, much like our remove functions did. And it returns a Boolean the same way. If it finds something, it returns true. If it doesn't find something, and therefore didn't remove anything, it returns false. So that's the same as we've been doing so far. All right. If this is what you knew how to do, then you might write a removal function like this. So you might loop through all of the items in the array list. Hopefully you're familiar with this fancy for loop syntax. You've probably used it before on arrays. If you haven't, that's fine. But this fancy syntax loops through all of the items in the array, and you can access them as you're looping through them like so. So if I.value is equal to n, then we're going to call r.remove on our item that we just found. And if we get to the end without finding one, then clearly it is false. And we could even return r.remove here, which we actually know is going to be true, so we could also do this instead. Those are logically the same, because if we've found the value, well then it should be removed as well. This is bad because it's actually O of n twice. We're incurring O of n once to find the value that should be removed. We're looping through all of the items and then finding the one with the value that we want to take out. But then it incurs O of n again because the ArrayList implementation doesn't have that information. It's not smart enough to pick it up. So it has to, once again, find that item in the ArrayList. It's actually going to execute essentially the same loop to then find that item and then remove it. So we're incurring an extra O of n when we don't have to. Well, how can we make that better? If we had access to the index, then instead of passing an item argument, we could pass the index. And when we pass the index, then all it has to do is remove that item and shift everybody else over. Yeah, I should actually say we're incurring O of n 3 times because I didn't even accommodate for the shift. So first we find the item with that value, then we call this remove, which finds that item again, and then it actually does the removal, which shifts them all over. So 3 times. So in the better version, up there? Yeah, there it is, okay. In the better version, we would just loop through, which allows us to keep track of the index. All right, and then as we loop through, if the index of that value is the one that we're looking for, then we are going to remove it. And here we have to return true. Now you'll note that you can't return this remove function. This remove function, the one that removes an index, is a void. It doesn't return anything because it is either always successful or it goes out of bounds. If you specify an index to remove, it's either going to remove it or it's going to go out of bounds and cause an exception. There is no failure to remove an index. It can't not find the item. It's guaranteed to find the index. You can't not find an index. And much like our remove from the array example, what did we find here? Very similar to our sorted one. Yes, quite similar to our sorted one, although this works even for array lists that aren't sorted. The values are all left shifted beyond the point that is removed. So even though array lists aren't sorted, they do this no gaps functionality that we had added to our arrays in the demo. And rather than doing what we did, where they fill the gaps by taking a spot from the end, ArrayLists do what we did in the sorted implementation, where they backfill those gaps by shifting all of the items to the right over by 1, so that they are now scooted over and that gap is full. The reason for that is because ArrayLists are implemented with the assumption that order matters. And so unlike in our arrays example, where the item from the end was constantly getting pulled into spots and backfilling, in the ArrayList you can always be sure that the rest of the items, the ones that aren't removed, are going to be in the same order before and after the removal of a different item. This is advantageous for a number of reasons that we're not going to get into. Alright, so that was removing a value, one value, and that was good. But if we made a little bit of a change to this to remove all the values that matched that integer n that we're looking for, so if we wanted to remove all the items of that value, then all of a sudden this would actually be broken. I'm going to show you what that would look like. So if we did this, and we didn't return after we removed the item that we were looking for, because we want to continue and see if there are any more. So if we're trying to remove, let's say, 3, we're going to remove the first occurrence of 3, and then we're actually going to continue and remove all the other occurrences of 3. So maybe there are a bunch of others in the array list. Then we don't return, and we're going to continue going through the loop and looking to see if other items have a value of 3. This function is actually broken. And the reason it's broken is because when ArrayLists remove something, all of the other values shift to the left. And so if you started with, let's say 4, 5, 6, 7, 8, 8, 8, 8, 8, and then 4, something like that. Okay, and your indexes up here are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, if you remove 8, here's what happens. Your for loop visits this item, not an 8. Then it visits this item, not an 8. This item, not an 8. This item, not an 8. This item, it is an 8. So what happens next? Your for loop is right there on index 4. Your for loop is going to go ahead and remove the 8. You're going to be left with this. 1 less 8. All the items scoot over to accommodate. Remember, these empty spots at the end are there, but we don't see them. Those are all under the hood. Your for loop will now happily advance to the next item, having done its job in that iteration, and will now completely skip over this extra 8, which has now occupied that spot. So because all the values shift to the left, you actually have to visit spot 4 again, because spot 4 is now a new item. It's not the item that you just removed. It's the item that used to be in spot 5 and has now taken its place. So to fix this isn't too hard. We just have to step back after we remove something. We could do this, and just walk back a step after removing the item. If we do that, then we are now properly visiting all of the items in the list as we remove them. And this is fine, but it's awkward and it's kind of difficult to read. And if you do this a lot, and especially if you do this in like a nested structure, it gets really confusing. And it's not really, let's say, canonical. So let's look at the canonical and correct way to remove an item as you are iterating through an array list. The correct way to do it is with an iterator, another typed kind of item. The iterator is something that you can get from the array list. So there's this r.iterator call that returns an iterator for you. And when you import it, be careful to import the correct one. It's the one that just comes from the java.util library, not the iterator that comes from other libraries, which is actually not the first choice for some reason, so be careful with that hiccup. You want the one from java.util. And if you'll hover over the iterator's description, I think it's pretty apt. It says that it allows the caller to remove elements from the underlying collection during the iteration with well-defined semantics. So this is essentially the purpose of iterators, is simply to be able to loop through a list-like structure. So in addition to ArrayList, other objects that inherit from list do the same thing. They also have iterators. It allows you to loop through them and safely remove an item without running into weirdness like you get here. So the syntax for looping through an array list using an iterator is to see while iter.hasNext, which returns true if there's another item in the list, false if you're at the end of the list, and then you get the next item by calling iter.next. This actually advances the iterator to the next item. So until you call next, it doesn't advance. HasNext doesn't advance it, it just checks if the next item is available or not, and then next actually moves you to the next item. The iterator visits one item at a time in this way. And then if that item's value is equal to the one that we're looking for, instead of using a remove function on the array list like this, you use a remove function on the iterator, a remove function that actually takes no arguments, which is a little weird, isn't it? And what it does is it removes the last thing that the iterator had visited. So whatever the last thing that it had visited with next, that's the thing that it will remove. And it also only lets you call it once for every time you call next. So it handles all of the shifting for you. It handles the fact that something backfills the spot that you were just in. And next time you call that next in the next generation of the loop, it will move on to the actual next item and not the skipping an item, moving ahead kind of deal. So this is the canonical way to remove something while looping through. Anytime you want to loop through an array list and you think that you also might be removing things as you go, this is the way that you have to do it. This is a little bit awkward when you also need the index, because obviously you don't have the index here. So if you also need the index, you can always do something like this, where you keep track of the index in each generation of the loop. Just remember that if you remove something, you might have to go back depending on how you're using the index in your application. In this case, we don't care about the index, so that's not necessary. And in most cases, when we're using ArrayLists, we don't care about the indexes of the individual items. But remember that if you try to remove using an item rather than the index of an item, you're incurring an O of n removal instead of the much cheaper removal that just has to shift the items over. You're incurring a removal that also has to find it and then shift the items over. So always prefer to remove by index instead of providing the value and having to look for it. Okay, so that's our remove all values good version. We've got our remove value bad. We've got, what are we missing? We're missing remove sorted. Okay. For remove sorted, we're going to have to write a search again, because it's more efficient if our search is more efficient. The faster we can find the item, the better. And we can actually rewrite our old search from the array demo. Let's go find that guy, our old binary search. So this should be a good exercise in copying and adjusting it for an array list. I'm going to take out all the comments and all the other boilerplate. Take out the print statements. I don't need the count anymore. That was just for the print statements. Take out that too. Okay. So what do we need to change in order to finish this? Remember, I had mentioned that it was more efficient to start our endpoint at the next spot instead of the end of the array where all those empty values are. Well, that's still true here, but remember, accessing the next spot is now very easy. And then, of course, accessing an index is pretty straightforward, too. We're just going to use that get function and pass that same I along. Likewise here. And there we go. We've converted our binary search from arrays to now use in ArrayList. Not a lot of change had to happen here. Again, this assumes that the insertion happened in sorted order, too. Okay, what were we working on just now? What are we doing? We're doing remove sorted, right? Okay, so that's also going to be basically the same. We've got our remove sorted here, right? And before, most of the body of the function was accommodating the left shifting, but we know we don't have to do that now. We do have to do this part. So we've got to do the if it was found part. That's still true. So our search will still return our default, or -1, if it didn't find the item in the list. And now we just need to do the actual removal part. Do we need to do any of this left shifting, or is that all handled under the hood? Let's think. What can I do? Well, I have the index now, right? I have the index it was found at. That's what search sorted returns me. So if I just remove it, well, yeah, that left shifts all the items beyond that point. And now I'm done. I also want to return true here to indicate that it was found and removed, as I did for the others. I didn't do it for the all values ones, just to simplify it, but I did it for all the ones that remove a single value. And there you go. I can now find an object in the list and remove it. All right, the last one that we'll cover, I think, is searching the unsorted list. So here we have to decide what kind of loop we're going to do. Are we going to use an iterator? Are we going to use this for loop? Or are we going to use the fancy loop? Where did I have my fancy loop? I think it was part of insertion, maybe? There it is. There we go. Should I use my fancy loop instead? My item loop. Well, remember that the most efficient way to remove something is by its index, so that the function that removes it doesn't have to waste time searching for it again. So while I could write my search function to return the item that it found, it would be better if I return the index. So I'm going to use the loop here that allows me to track the index as well. And where is my search unsorted function? There it is. So I'll loop through, and this part's really the same. If the item at that index is equal to n, then I am done. I have found it. And I can return I here. And so that returns the index that I was looking for and allows me to now quickly remove it using that index. Alright, I think that's good for ArrayLists for now. And then next time we will use our array and ArrayList knowledge to build a couple of fancy new data structures on top of arrays and ArrayLists. But I guess before we conclude for the day, let's go and try out these last couple of removals. What did we do? We had a remove sorted, and that triggers if is sorted as true. Let's give that one a go. So let's change, use alt doesn't matter. We're going to change this to is sorted as true. That's already good to go. Save everything, and let's insert 4, 5, 6, 7, 8, and then let's remove 4, 5, 6, 7, 8. And there you go. They are removed. And add some more items and remove. Let's say we're going to go for this green 3. What got removed? Not the green 3. Let's go for this green 3 again. What got removed? Not the green 3. Go for the green 3 again. There it goes. And now the purple one. Remember when we were talking about binary search earlier, I mentioned that it's not necessarily going to be the first occurrence. And last time, the boxes didn't correspond to a particular item. They were just bound to that slot. So let me add a bunch more 2s here, just for demonstration. Which of these 2s is going to get removed? Well, I can tell you this. Because of the way the binary search works, it's going to search the midpoint first. So the midpoint, maybe I made this example a little bit too big. It's going to be one of these ones in the middle here. If this is, what are these, 3, 9 per row, and I got, that's 9, 18, and 27, and then, okay, too much math here. Let me actually start over. Let's go 9 here. Which of these 9 2s is going to get removed? It should be this purple one right in the middle, because that's the one that the binary search is going to visit first, and lo and behold, it is that purple one. Now, in the second generation, which of these 2s is going to be removed? Well, it's going to round down for the midpoint, so it should remove this greenish colored one right there. And no, it actually rounded up and removed the purple one. Okay, well, now I have an odd number of items again, so it's going to be the green one. And now I have an even number of items again, and now I know that it rounds the midpoint up. So it's going to be this pink one next then, right? And there it is, and then it's going to be the blue one next. So it's not necessarily predictable, but all of the remaining items stay in the same order, so it is stable. Okay, yeah, with that example, I think that's good to go. I will see you next time.